Okay, this morning we're going to go through kind of an exam prep, just kind of go back over the last few chapters. So exam 2 will be Friday. It's going to be during the normal class time. You'll have 60 minutes, so it's a little over class time. It's at 30 questions. So that's 3.3 each. It gives you about 2 minutes per question, which should be plenty of time on the test. And it's going to cover chapter 6, 7, and 8. If you look at the learning outcomes on Canvas, that'll give you a good outline of what I would expect on a test. And so if we look at the learning outcomes, so today what we'll do is we'll just go over some practice. I'll put some questions up and then I'll let you take a minute or two to answer those. So first, let's start way back in chapter 6. If you have any questions, either interrupt me or I'll put them in the chat. So remember, we started with just a simple what is homolytic and heterolytic. So let's take a look at a couple of examples. And just label these once you've figured them out. Okay, that wasn't quite a minute, but let's see. So in the first one, right, this is going to be homolytic. If we show the arrows, right, each one of these get a radical. That's homolytic, right? We're evenly splitting that. In this one, both electrons are going towards the bromine, so we end up with the anion and the cation. This is heterolytic, right? So uneven breaking of that bond. And then this one's a little different, but we have a pi bond. The pi bond is picking off a proton, right? So we're both electrons are going from the pi bond, giving us a positive charge, taking the positive away from this, and this is also heterolytic. Okay. So going all the way back to where we started.
Can you scroll back up for a second, please? I'm sorry.
Mm-hmm. Yeah, no problem.
Okay, thank you.
And remember, in this book, they break out the mechanisms into different types. So when we're drawing our arrows, so one of the things is understanding mechanistic steps. And so you'll need to review those steps. We'll go over it today, but make sure that you understand what those are. I'm going to draw several of mechanism types. What I want you to do is tell me whether that's a proton transfer, right? A loss of leaving group, a nucleophilic attack, or a rearrangement. So I'll draw a few reactions here, and then afterwards I'll wait for a little while and let you show the answer. Okay, it looks like that's all I'm going to be able to fit on the page. So let's stop right there, and then I'll do one more. Again, label the steps with those 4 possible mechanistic types. Okay, let's take a look. That was about 45 seconds. So here, if we look at these, so this first one, we've got the lone pair of the oxygen going to the proton, right? The proton here to form the protonated alcohol species. So this one is going to be a proton transfer. Okay. Proton transfers look a lot like nucleophilic attacks, except they're specifically with protons. So whenever the engagement, the interaction, the mechanistic step really is just involving a proton, then that's a proton transfer. You could think about this as nucleophile attacking electrophile, but that's a proton. So we refer to it as a proton transfer, okay? In the second one, we've got a methyl group that is shifting the carbon skeleton. So since we have a change in the carbon skeleton, whether that is an actual change in the carbon skeleton or a 1,2 hydride shift and moving over, this is going to be a rearrangement. Okay, and here we could refer to this as a 1,2 methyl shift because we are moving a methyl. Okay. Questions about either of those? This last one, we're putting several together. So we've got more than one step. So each step is going to have one. In the first one, we have a nucleophile attacking electrophile, but that electrophile is a proton. So this one is going to be a proton transfer. So proton is changing positions. Then in the second step, we have the water, the protonated water here leaving to give us the carbocation. So this is loss of the leaving group. Okay. All right, let's do one more. Let's give that one. Okay, in the first one, right, we again have a nucleophile attacking electrophile, but this electrophile is a proton, so we're going to call that a proton transfer, right? We're moving a proton. In the second step, we have a nucleophile attacking electrophile. In this case, right, it's attacking electrophile, it's not a proton. This is going to be nucleophilic attack. Okay, we can reason that I think this is helpful is that you can think about all of your mechanisms that we went over in chapter 7 and 8 as, you know, proton transfer, leaving group, nucleophile attack, rearrangement, right? You can put those all together and you can actually turn every mechanism into a set of those words. Okay, let's look at rearrangements. Okay, I'm going to put a few carbocations here. You tell me if it's going to rearrange. If yes, then tell me what the rearrangement product would be. And let's take some time. Again, if you have any questions, put them in the chat or interrupt. Okay, that was about a minute. Remember, you're going to have 2 minutes per question on the exam on Friday. So I'm going a little faster. So the pace we're doing here is more so we can get through lots of practice, more than what you're really going to see on Friday. So if we look here at rearrangements, what are we looking for rearrangements? A carbocation rearrangement, right? We want to increase stability. We can either do that with a 1,2 hydride shift, or we can do that with a 1,2 methyl shift. If we start this first one right here, we have a secondary carbocation if I shifted, and now there's doesn't look to be any hydrogens, methyls, but if we looked at our hydrogens, if I shifted any of those 4 hydrogens, am I going to increase the stability of this molecule, this carbocation? No. So therefore, in this case, no rearrangement, right? There's no advantage to a rearrangement, so I'm not going to have a rearrangement. In the second one, we look at it, we do have a methyl, right? This is secondary again. We could move this methyl, but if we move this methyl, we would end up with a secondary, right? So if we did something like, so let's draw some possibilities. Sometimes that's the best way to answer this. Is that more stable? No, it's exactly the same thing, right? So that's not going to work. We could potentially move one of those hydrogens. If we move the hydrogen here, right, to move a hydrogen there, that's also a secondary, right? So that doesn't work or doesn't give us anything more stable. But if we do the other side, right, and we do a hydride shift this way, right, 1,2 hydride shift, this gives me a tertiary substrate, a tertiary carbocation, and so that's more stable, right? So that's my answer, right? I can make a more stable carbocation. It's through a 1,2 hydride shift to form the tertiary carbocation. Okay. And this last one down here, we have 2 hydrogens, nothing on the other side. So let's look and see what happens if we do a shift. If we did the shift, we'd end up here. So this is primary, this is secondary. So that's a stabilization. But is it just a secondary? No, this is a stabilized secondary, right? Because I can delocalize that carbocation now through the ring. And I could draw several resonance structures of that same carbocation. Okay, so with rearrangements, we need to be looking at those. Thanks for the answer. Yes. So the first one, no. Second one, yes, we do a hydride shift. Third one, we do a hydride shift. We get a stabilized secondary, which gives us the product. So watch for being able to be adjacent. So watch for allylic, right, and benzylic positions. This one was benzylic. Okay, so even if it was tertiary to tertiary, I mean secondary to secondary, if the secondary was allylic or the secondary was benzylic, that would make it more stable, and that would be a potential rearrangement product. Okay, questions about rearrangements?
For the second rearrangement, that hydrogen shift, that hydride shift, did that come off of carbon 2?
Yes, so it's this one right here. So that hydrogen shifts to get to this position.
Perfect, thank you.
Okay. Mm-hmm. Right, remember that the rearrangements you know right now are all carbocation rearrangements. There's some other rearrangements that you'll see in organic too, so if you continue into that course or have to continue into the course. Okay, let's look at labeling. Nucleophiles, electrophiles, and leaving groups. So I'll draw a couple of reactions.
Why did you label the hydride shift 1, 2 instead of 2?
Because it's 1, 2 because of where the hydride shift is moving. They're all referred to as 1, 2. So this is the, let me pick a different color. So this is 1 and that's 2. So the numbering of the carbon system is different. All of the, you're always moving a hydride from a 1 to a 2 position. You're always moving a methyl from a 1 to the 2 position. So you're always moving a 1. There was an idea in organic mechanisms. There was a potential, they saw a 1,3 methyl hydride shift, but it actually turns out they were able to prove that a 1,3 hydride shift was actually just 2 1,2 hydride shifts. It was debated for decades, and it took a while to figure that out. But so they got this name 1,2 because at one point there actually was a theory that there were others, but it has to do with you're just moving it 1 carbon. Okay. The nomenclature on this, which we'll do some nomenclature in a second, this would be 2-methyl. So we actually took that 2nd carbon position hydrogen to a 3rd carbon position hydrogen, but it's still known as 1,2. Okay, let's look. All right, so I'm going to give you a few reactions. You tell me what the nucleophile, electrophile, and leaving group is, and make sure you notice and let's get away from hot pink. Oh, and if you hold that down, it makes you curve. Notice the direction of the arrow. Because that's also going to help you figure some of this stuff out. And I better stop there because we can't put more on the screen. Give you a little time.
On the bottom reaction, is your arrow going down because that has a significance, or is it just because you can't fit it on the page?
Just can't fit it on the page.
Okay.
Yeah. So it's just a continuation. Sometimes you'll see where I'll actually take them around a corner. Okay, let's take a look at the first one. All right, if we're looking at this, what's going on here, remember sometimes we need to focus on we should look at the reagent. So that can help us see what's going on. And with that negative, that looks like a nucleophile, and it is, right? So I have an oxygen negative, that's nucleophilic, right? Over here, I've got a partial positive, right, and a partial negative. That makes this position my electrophile, and that makes this tosylate, right? Tosylate's a good leaving group, right? And again, it'd only be a good leaving group if it's stable once it's left. I didn't show the tosylate over here, but I could have. Usually you're always only focusing on the products. So in this one, our labels are nucleophile, electrophile, leaving group. There's no second reaction, so that's all I needed to label. When we look at this next reaction, I've got my bromine, which, bromine has an instantaneous dipole. So potentially I could have electrophile leaving group. My nucleophile really only has, this whole reaction really only has one thing, which is that pi bond is my nucleophile, right? So that's my nucleophile. The bromine becomes my electrophile, and the other bromine becomes the leaving group. So labeling those are my labels. If I look at then this has a second reaction, and that arrow going down again has no significance. But this bromine negative, that's negative, right? Negatives and pi bonds are nucleophiles, things that have electron deficiencies. And again, here I could have pointed at either of those two groups, and then this bromine becomes my leaving group, but it's really better to say, because the bromine's not actually leaving, I would say that bond is my leading group, right? I'm breaking that bond, and that bond is going to give me, and that's a horrible L. That bond is what's really leaving there. Questions about labeling these? Right, that's a good, it's a good way to help you. What we've looked at here is really kind of thinking about your base mechanisms, because many of your reactions you're going to be able to actually work through a process to figure out what's going on. Okay, let's do a little nomenclature. We didn't spend a whole lot of time on it. Some of it's pretty basic, mainly because it goes back to just naming alkanes. But we do need to go ahead and look at some nomenclature for alkenes, specifically some of the stereochemistry. Now, these last two, I'm going to ask you to tell me whether it's E or Z. So let's take a little time on this one. Give you 2 minutes, and then we'll go through them. Let's take a look. In the first one, how long is our carbon? Our carbon chain is 5, right? So 1, 2, 3, 4, 5. That gives us pentane. A chlorine is not a functional group, so we're not going to change the functional group. And then if we look at our carbons, we could either go 1, 2, 3, or we could go 1, 2, 3, 4. 2, 3 is better than 3, 4. So we'll go with 3 chloro. 3 chloro, 2 methyl. And give myself enough space. Okay. And no stereochemistry is shown, so I don't have to worry about R or S. In the second one, we have 5 carbons, but this time we have a double bond, but the double bond could be anywhere, so it is appropriate to put 1. So this is 1 pentene. And the next one, we have 5 carbons, so cyclopentene. Now it's in a ring, so therefore the ene here has to be 1 and 2. So it's assumed 1 and 2. I don't need to put 1 cyclopentene. Right? And then since that's 1 and 2, that means the methyl the lowest it can be is 3. So this is 3-methylcyclopentene. Okay, so the ene in the cyclics, it's well, we haven't got the alcohols, but when we get to alcohols, we'll see that in cyclics, alcohols don't need to be numbered because by convention, they are 1. Here, the double bond is not numbered because by convention, it is 1 and 2. Okay, if we look at the next one, we have 1, 2, 3, 4, 5, 6. So that gives us hexene. And it is on the 3rd carbon. So this is 3-hexene. Now I can name this as trans, or I could name this as E. If we look at how to name it as E, first we just divide this down the middle, right? And then we're going to look at our 2 groups, and there's a hydrogen here and a hydrogen here. And I'm going to use the same rules that I used for there's only a few common names. I'm not going to focus on common names. Like T-butoxide, right, for the tert-butyl potassium. So there are some common names, but I'm not going to specifically ask for some common names. Let's put it this way: if we've been using the common name all the time, then be aware of that common name. I'm not going to specifically ask you what the common name for, let's say, pentine or isobutylene, if that makes sense. Yeah, so whenever it's in a cyclo, the preference for the cyclo is 1, 2. So that's part of the naming. Right now, if you have 2 double bonds in a ring, then you would have to put the number on those because the second one doesn't hold that. But when there's only 1 double bond in a ring and it's named as the double bond, then, you know, as an ene, then that is the convention is 1 and 2. Okay. All right, so if we look here, getting back to E and Z, so what we want to do is use the same priorities that we used in R and S. So really what we're comparing here is that carbon and that hydrogen, right? The carbon has a higher priority, so that gets 1. The hydrogen gets a lower priority, so that gets 2. On the other side, again, we have a carbon and we have a hydrogen. We don't have to worry about the CH3. We just go 1 carbon at a time. So that gets a 1 and that gets a 2. And then what we can do is look, you know, down that ring, and this is a bad color. But then what we do is look and see where those 2 are. And we see that our 1s, right, are on opposite sides, and that's opposite, right? Z is same side, so E, so E3-hexene. In this case, we can use either trans or E, right? Either of those works. E is kind of like the Queen's English, right? It's more proper, but both of these are fine because it's only a di-substituted species. Is there a chiral center in the cyclopentane? There would be a chiral center in the cyclopentene, but it is not identified. So this position right here is a chiral center, but it's not identified, so you don't have to name it. Okay. If we look at our next one over here, we have 1, 2, 3, 4, 5, 2, 3, 4, 5, right? So this is going to be a pentene. We need to say where that is. So it gets priority. So therefore it's going to be 2, which then is going to make the methyl 3. Right? So we're naming it as the ene. So ene gets priority. And then here we cannot use cis and trans. Right? The cis and trans doesn't work because I have 3 substituents. So what I want to use is ENZ. And again, I'll divide this down this way. I'll look at my priority groups. And here I have a methyl with 3 hydrogens attached. Here I have a carbon, right, with 2 hydrogens attached. So these 2 are carbons. So then I have to look one more. This carbon only has 3s attached. This is a carbon, 2 hydrogens, and a carbon. That makes that 1. That makes that 2. Here it's a carbon and a hydrogen. So that makes this 2. That makes that 1. right? And then if we look down here, where are my 1s and my 2s? And my 1s are on opposite sides. So this becomes E, right? So this is going to be E3-methyl 2-pentene. So when I have more than 2 substituents, I need to use E and Z. When I only have 2 substituents, I can either use trans or E. E is a little bit more universal. And like I said, kind of like the Queen's English versus, let's say, what I speak, which is Texan/Cajun English. So, okay, questions about nomenclature. All right, let's get into predicting some products. So most of what we covered, right, this really kind of gone over the basics now, mechanisms, things like that. We covered those so that we could cover a lot of reactions. And so predicting reagents, predicting products, selecting reagents is going to be a significant portion of the exam. Okay, so I'll put a few on here, give you some time, and you tell me what the product is. Okay, so let's take a look at these 3. Okay. I'm gonna let you finish this one and then I'll go back and answer about E and Z. Okay, let's go ahead and take a look. In this first one, right, we have cyanide here, so it's negative, positive, acetone, right? So this is a good nucleophile. It's not basic, right? So therefore, this is looking like an SN2. We have acetone, which also suggests SN2. Why does that suggest SN2? This is an aprotic solvent, right? Aprotic solvents favor SN2. And then here we have a leaving group, right, at a secondary position. So all of this suggests SN2. It's a possibility this is going to attack from the backside. And so therefore my product will be the SN2 product, which will have the cyanide coming from the back. Okay. If we look at the next one, we have hydroboration oxidation. Okay, so the BH3, we're going to add the boron and the hydrogen to the same side, and then we're going to eliminate the boron to give us the alcohol. So I can go ahead and show some stereochemistry here. Let's do it this way. Right, and we will have the hydrogen and the alcohol on the same side. So this is anti-Markovnikov, right, and syn addition. On the next one, we're adding our tosyl chloride. Now the oxygen reacts with the sulfur, so therefore there's no reaction at the carbon, which means that the first product, there is no change in stereochemistry, right? So it's not like there's inversion or retention. There is no change in stereochemistry because all the reaction is happening at the oxygen, not the carbon. Then in the next step, I have an SN2 process, right? Really good nucleophile, not basic, aprotic solvent, really good leaving group. So therefore, then I have a reaction occurring at the carbon and I get inversion, okay? You know if something is syn or anti, if the two groups are adding. So in a carbocation, right, there is neither. It's not anti or syn because you can have both. So you could say it's both syn and anti in a carbocation mechanism. But if it's not a carbocation, then are we adding both groups to the same side? Or are we adding them to the opposite sides? And you could say that you memorize it, but if you work through the mechanism, you'll see this, that the mechanism is that the boron and the hydrogen are adding at the same time, right? This is, let's use red. This is coming out and attacking here, and this is coming down all in the same step. And since it's all occurring in the same step, then I end up with my hydrogen and my boron coming from the same side. So it's part of your mechanism. Okay, let's go back before I forget on the E and Z. So in the E and Z here, notice that when we perpendicularly bisect it so that we can compare these two groups, and we see that this carbon is attached to 2 carbons and another carbon, that gives its priority over a carbon attached to 3 hydrogens, right? So using RNS rules. And then here, if we look at it, we have a carbon and a hydrogen, so we see our 2 ones. Now, when we go along the plane, right, if we go along that here, where are my 2 ones? Are on the same side or opposite sides? Well, they're on opposite sides, and that gives me E. So think about Z as same side if my ones had been on the same side. Now, this one is counterintuitive because you see the 2 methyls and you think, oh, it's trans, but you're thinking about trans wrong. Trans is only for 2 substituents. When I have more than 2 substituents, I have to use E and Z, and then I have to use the RNS nomenclature. So it's not that I have 2 ethyls, and so they're to do ethyls give me cis and trans. It's that those 2 carbon groups are either on the same side or opposite sides. So if you go to 3 or 4 substituents, you have to use E and Z, which is the RNS priorities, and then you have to determine, are those 2 priorities on the same side? And in my case here, right, the orange, and they're on opposite sides. I'm not going to focus on bicyclics this time. Bicyclics take a little bit more explanation. I did not do that in class, so it won't be on exam 2. If we have time at the end of the semester, we'll cover bicyclics. You might see them. Lots of bicyclics have common names in medical areas. So the likelihood of you naming a IUPAC name for a bicyclic as a medical professional is pretty low because you're probably going to know the common name. Medical is still heavily biological, which still is heavily common names, which you have to memorize. But if we have time, we'll go through that for this test. Don't worry about that. Let me see other questions we have. Right, so you do need to know for every reaction, you need to know, especially every addition to an alkene, right? Every addition to an alkene, you need to know, is it anti-Markovnikov or Markovnikov? And is it syn, anti, or in the case of carbocations, right, both? In the second reaction, how it changed is that I added both of those to the same side. So I'm just adding, since these are on the same side here, they're both going to be going down. So you can think about what I said is that the BH3 BHs here added to the top as I was shown at the bottom. No, concerted reactions may be syn or anti. Okay. Well, let's look at that example. That's a good question, and it's a little bit more complicated. If we look at this one, well, let's do a cyclic. Cyclics are easier. So let's do a cyclic. Okay, so let's say we take the bromine, and let's do water. So yes, the first step of this is syn, right? So it is syn, but can I stop at this brominium ion? No, so I can't stop at the brominium ion. I have to go on. This is not a stable species. So although this intermediate is syn, the second step, which has to occur because this is not stable, it's going to break open, right? We get then the addition here, right, of the OH. And because I'm an organic chemist and it irks me to stop mechanisms without them being completed, I'm gonna have to show the final proton transfer. So we do the proton transfer. And so what is the result of, what is the overall result of this reaction? Remember, I can't stop at the brominium ion. Well, are they on the same side or opposite? Well, they're opposite. So this is an anti-addition. Because I've added my bromine and my OH to opposite sides. Okay. Yes, so up here, it's the oxygen that's doing the attack on the tosylate, not the carbon. So there's no reaction at the carbon. Right. Okay, let's try a couple more of these. We're running out of time. Let me see if there's anything we really need to make sure. Okay, let's do select a mechanism. Remember, I have office hours this afternoon. Let's do these real quick. Okay, tell me if it's SN1, SN2, E1, E2. And since we only have a couple minutes, let me go ahead and give you the answers here. This first one, we have a weak nucleophile base, right? Weak nucleophile base, we have a tertiary position. This is going to be both SN1 and E1. Remember that SN1 and E1 are almost always in competition. The only real example of that is dehydration of alcohol, which gives you E1. And so here, weak nucleophile base, tertiary position, SN1, SN2. Second one, we have a good base, poor nucleophile. Why is it a poor nucleophile? Because it's bulky, right? It's sterically hindered. So in this case, I'm going to get E2. Right, and in this case, because that's the bulky, I'm going to get the Hoffman alkene. Next one, I have a good nucleophile. Right, I've got an aprotic solvent. I've got a secondary position. Is the nitrile a good base? No. So therefore, we get SN2. Okay, so you'll need to be able to determine the SN2 and the all the different mechanisms. Okay, the other part of knowing the reactions is predicting the reagents, right? So you'll need to predict the products, but you also need to predict the reagents, and we don't have enough time to go through some of those today. But you know, you should be able to answer something like, how did I form, you know, this? Or how did I go from this to this, right? Or how did I go from this to that, right? And so I won't be able to give you enough time to practice these, but in this first one, this is an anti-addition of 2 hydroxy groups. That means that I'm doing a peroxy acid, you know, MCPBA or any of the peroxy acids. And then second step, I'm doing the sodium hydroxide, right? So I'm doing a ring opening. Oops, we haven't seen that one yet. So let's do H3O plus. That's the one you've seen, right? We do the ring opening with the acid and water. This next one, we're doing ozone followed by, you know, a reducing agent such as DMS or the zinc and water. And then this last one, I've got 3 choices, right? But this is a Markovnikov addition, right? But it also has no rearrangement, right? I haven't moved my tertiary group there. So for that one, I'm going to need my oxymercuration demercuration, right? And you got to put it in water because the water actually comes in that first step. And then the hydride gets just rid of the magnesium. I mean, the mercury, not magnesium, mercury. Okay. All right. So test is on Friday. We have some office hours this afternoon. The learning outcomes are up. I added some more action center problems with the answers. So do a lot of practice, get some sleep. And then there is no respondus for the test. You just go in. You got 60 minutes once you start. If you did have an accommodation, I do need you to let me know about that and what the accommodation is. So far, I'm only aware of 3. Okay. Yeah, there is some entropy and some enthalpy on there. Yes, I just did not practice that. Okay.
Can you scroll up, please?